welcome to the deep dive. Today, we're taking on a big one. We're tackling the APES Unit 4 review.
It's a huge unit.
It really is.
Yeah.
It's not just a test. It's this foundational check that expects you to know everything from the Earth's core all the way up to global weather systems, soil. Even population ecology gets pulled in.
That's absolutely right. And the sources for this are, well, they can be overwhelming. You've got plate tectonics, thermohaline circulation, adiabatic heating. It's a lot of complex processes.
So our mission today is to cut through that.
Exactly. We're going to pull out the essential, the high-yield connections and mechanisms that you really need to understand to nail the test. Think of this as your shortcut to the processes, not just memorizing the definitions.
Okay, let's unpack it. We're going to start from the bottom up, literally, with the rocks beneath our feet, and then work our way up into the atmosphere and the climate patterns.
Sounds good. So let's start with the lithosphere. That's the solid, rigid layer, the Earth's crust, and the very top part of the mantle.
And the key thing is, it's not one solid piece. It's broken up into plates.
Right, and those plates are always moving. So what's the fundamental driver behind all that movement?
It's got to be those convection currents way down in the mantle, right? It's like boiling water where the heat rises and falls and it just drags the crust along for the ride.
That's the engine. And that movement leads to three distinct ways the plates interact, which, you're right, are guaranteed test questions. The key factor in all of it is density.
So if you have a dense oceanic plate meeting a less dense continental plate.
The oceanic plate always loses. It's denser, so it sinks down beneath the continental plate. And that process is called subduction.
And that subduction is a big part of the first boundary type, the convergent boundary. That's where plates are colliding.
Right. It can cause mountain building like the Himalayas, or if subduction is happening, you get those coastal mountain ranges and deep ocean trenches.
Okay, so next is the divergent boundary. That's just the opposite, right? They're moving apart.
Exactly. Pulling apart. This is usually happening on the ocean floor where magma wells up and creates new crust. You get those mid-ocean ridges. It's literally seafloor spreading.
And the last one, the one that sometimes trips people up, is the transform boundary.
Yeah, they aren't colliding or separating. They're just sliding past each other horizontally. All that grinding builds up immense friction.
Like the San Andreas Fault. It's not a mountain range. It's a massive crack, a fault from that movement.
And that grinding is what releases energy as earthquakes. It's so important to remember how we measure them. The Richter scale is, it's logarithmic.
That's the key insight, isn't it? A magnitude 7 isn't just a little stronger than a 6.
Not at all. It's about 32 times more energy. It's an exponential increase, which has huge implications for, disaster planning and building codes.
We should probably nail down the terms. The focus is the actual spot deep underground where the rock breaks.
And the epicenter is the point on the surface, right above the focus.
Yeah.
Simple difference, but you have to get it right.
So that connects to volcanoes too. You mentioned subduction.
Yes. So when that oceanic crust full of water sinks down, the heat and pressure turn that water into superheated steam. It expands. It looks for a way out.
And it finds a vent, creating a volcano.
Exactly. And all of this, the melting, the pressure, the cooling ties directly into the rock cycle.
Right, this constant transformation, let's run through them. First is igneous.
The starting point. Formed from cooled magma or lava. Think granite.
Then you have metamorphic rock. That's when any other rock gets cooked by intense heat and pressure, but without fully melting.
It just changes its structure, like limestone turning into marble.
And finally, sedimentary rock. This is just bits and pieces of other rocks, sediment, that get compacted and cemented together over millions of years.
And if you're ever asked where fossils are found, this is your answer. In those layers. Think of the Grand Canyon. You can see the history right there in the strata.
Okay, one last piece of geology before we move on. Hotspots.
Right. The Hawaiian Islands are the perfect analogy here.
Yeah.
The hotspot itself, the plume of magma from the mantle, it doesn't move.
But the tectonic plate moves over it.
Like a conveyor belt. So it creates a chain of islands. The newest, most active island is the one that's currently sitting right on top of that hotspot.
Okay, great. So let's shift focus up from the bedrock to the thin, vital layer on top of it all, the soil.
Yeah, and it's so much more than just dirt. It's a living system, a medium for plants, a water filter, a habitat.
And its creation all starts with the parent material, which is just the bedrock underneath. But that rock has to be broken down first. That's weathering.
And you have to distinguish weathering from erosion. Weathering breaks the rock down. Erosion moves it.
So what are the types of weathering?
Well, you have mechanical weathering, which is just physical. Water getting in a crack, freezing, expanding, pop. Or a tree root slowly splitting a boulder.
And then there's chemical weathering.
Right, which actually changes the rock's composition. Think of acid rain dissolving limestone, or even lichens on a rock releasing acids that slowly eat away at the surface.
So once the rock is weathered into little pieces, erosion kicks in and moves that material with wind or water.
And all that action creates the soil horizons, the layers. For your test, you really want to focus on the top layers. The O horizon, which is mostly just surface litter, leaves and twigs.
And the A horizon, that's the good stuff, the topsoil. Rich in organic matter or humus. It's where most of the life is.
Below that, you get the B horizon, the subsoil. That's where minerals and chemicals from the topsoil get washed down and accumulate. Then you have the C horizon, which is basically just weathered rock pebbles.
But the quality of that topsoil, that A horizon, really depends on its texture. The mix of sand, silt, and clay.
Absolutely, and this is where students can get confused. It all comes down to particle size.
Sand has the biggest particles, so water just rushes right through it.
Right, plants can't get enough water, nutrients get washed away, it's too porous.
And clay is the opposite. Tiny, flat particles.
They pack together so tightly that water can't get in, so you get waterlogging, and the plant roots can't breathe, it's too compact.
So the ideal is loam.
The Goldilocks zone, a balanced mix of sand, silt, and clay that has good drainage, but also holds on to enough water and nutrients.
And since good soil takes, thousands of years to form, we have to protect it.
We do, and the sources point to a few key conservation methods. Things like using cover crops, planting something like rye after your main harvest to hold the soil in place over the winter.
And vegetative buffers?
Yeah, planting strips of trees or shrubs next to rivers and streams. They act like a filter, catching sediment and runoff before it pollutes the water.
Okay, so we've covered the ground beneath our feet. Now let's look up to the atmosphere and the oceans that drive our climate.
And there is one single principle you have to understand that drives almost everything.
Let me guess. Warm air rises.
Warm air rises and it holds more moisture. That's it. As that warm, humid air goes up, the pressure decreases, so it expands and cools. That's called adiabatic cooling.
And as it cools, it can't hold as much moisture, so the water condenses into clouds, and then you get rain.
Exactly. And the opposite happens when air sinks. It gets compressed, which heats it up, adiabatic heating, and that makes it hotter and drier.
This whole cycle is the engine for the big global weather patterns, like the Hadley cells.
A perfect example. At the equator, you have intense solar energy. So warm, moist air rises, it cools, and it just dumps all that moisture,
Creating the world's rainforests.
And that low-pressure band where it all happens is the Intertropical Convergence Zone, the ITCZ. It's where the trade winds from the north and south meet.
So after that air drops its rain, it's now cold and dry. What happens to it?
It gets pushed out towards the poles, but it sinks back down around the 30-degree latitudes north and south.
And since it's sinking, it's heating up and getting drier.
Precisely. And that is why the world's great deserts, the Sahara, the Australian outback, are located right around that 30-degree mark. It's not a coincidence.
And all this air isn't moving in a straight line because of the Earth's rotation. That's the Coriolis effect.
Right. It deflects everything winds, ocean currents, causing them to curve.
Let's pivot to the oceans then, because they move even more heat around the planet than the atmosphere does.
They do. And you have to understand the global thermohaline circulation. People call it the Great Ocean Conveyor Belt. It's critical for regulating climate.
Okay, so thermo for temperature, haline for salt. It's all about density.
Entirely driven by density. The key event happens in the North Atlantic, up near Greenland and Iceland. The water there gets incredibly cold, and because some of it freezes into sea ice, the remaining water gets extra salty.
And colder, saltier water is denser, so it sinks.
It sinks to the bottom of the ocean, and that sinking motion pulls warmer surface water, like the Gulf Stream, north to replace it.
Okay, but here's where it gets scary. The sources point out that the glaciers in Greenland are melting fast. That's a ton of fresh water.
A ton of fresh water. And fresh water is less dense than salt water, so it dilutes that area of the North Atlantic.
So if the water isn't salty enough, it stops sinking.
It stops sinking, and if it stops sinking, the whole conveyor belt could slow down or maybe even stop altogether.
And the Gulf Stream is what keeps northern Europe so much warmer than it should be for its latitude.
So the great irony, the paradox, is that a major consequence of global warming could be a rapid, localized cooling event. A mini ice age for places like the UK and Scandinavia.
That is a wild thought. Okay, another major oceanic shift we need to cover. El Niño.
Or ENSO. El Niño is basically a disruption of the normal pattern in the Pacific Ocean. Normally, warm water piles up in the Western Pacific, near Asia.
But during an El Niño, The trade winds weaken, and all that warm water sloshes back east towards North and South America.
And the impacts are completely different depending on where you are.
Right. Australia and Indonesia might get terrible droughts. But here, California might get some much-needed rain.
But for countries like Ecuador and Peru, it's a catastrophe. Torrential rains, massive flooding, it devastates their fishing industries. It's a perfect example of how interconnected these huge planetary systems are.
We went from the Earth's core, plate tectonics, soil, all the way up to global climate and ecology.
And the main takeaway for your test, really, is to focus on the drivers of these processes. Convection drives the plates. Density, temperature, and salinity drives the ocean currents. Adiabatic cooling drives the distribution of rain via Hadley cells. If you master the why, you'll master the unit.
And let's end with one last thought, building on that climate paradox we talked about. The idea that melting glaciers could, ironically, plunge northern Europe into a localized ice age by shutting down ocean circulation.
It's a powerful idea, and it raises a really interesting question for humanity. Given how fast our own environment is changing, often because of us, which strategy are we following? Are we behaving like the specialized, inflexible red panda, totally dependent on specific, stable conditions to survive?
Or are we behaving more like the generalist raccoon, highly adaptable, maybe a little chaotic, and capable of thriving in and even causing destabilized environments? Something to think about while you study. Good luck.